Good afternoon. Professor David J. De Los Reyes, former professor of electrical engineering, OP College in Asia. Okay, let's proceed for this afternoon, guys. My topic will be the derivation of the formula of a right circular cone by using hollow cylindrical method. Formula for taking the volume of a right circular cone by using hollow cylindrical method. Okay, let's proceed. Lesson number 71 on my channel under the topic Integral Calculus, under volume, under the subtopic hollow cylinder method applied to right circular cone. The significance of the topic for this afternoon is that I will derive the formula for taking the volume of a right circular cone by using the hollow cylindrical method. Actually, we are through with the volume of a right circular cone by using the circular disc. Okay? So, for this afternoon, I will now present the solution by using the hollow cylindrical method. So, actually, there are many solutions on how to derive the formulas. So, all the formulas under lower mathematics, it emanates from integral calculus. Okay, let's proceed. Problem. Derive the volume of a right circular cone using the hollow cylindrical method. Hollow cylindrical method, it is something like this. If we got a certain slice, vertical slice, then we try to rotate it around an axis. Actually, the resulting differential volume is actually a hollow cylinder. It is something like this on the isometric view. Okay? So actually, that's another variation on how to bring out the formula, derive the formula. Okay, let's bring out the Cartesian coordinate system. This is the y-axis, x-axis. We draw the circular cone now on the Cartesian coordinate system. We draw the right circular cone in such a way that it will be symmetrical with respect to the y-axis, meaning the center of axis is actually passes through the third or the vertex of the right circular cone, and it bisects the circular cone equally into two, meaning the area on the right is same as on the left. So it is symmetrical. So by using a hollow cylindrical method and by using a vertical slice, this is a vertical slice. Something like that. Okay? Vertical slice. We put it on the right, then we try to rotate that differential area one complete revolution. What will come out is actually a hollow cylinder. And the isometric view of that one, if we try to draw it, is something like this. There's a hollow at the middle. There's a hole. Okay, because under the circular disc, it was a solid thing, you know. But under hollow cylindrical, there's a hollow at the middle. There's a hole. As we rotate the differential vertical area, there's a hollow that will come out. That's why our topic is hollow cylindrical method. Okay? Let's try to draw the differential area. This is the differential area, vertical differential area. This point on the differential area is y higher, and this point is y lower. Okay? The radius or the distance of this of the differential area with respect to the axis of rotation. Okay? This should be y, guys. This should be y. Okay? The rotation will be something like this. Okay? The distance of the differential area from the axis of rotation is x. It is an abscissa, okay? It's measured horizontally, so it should be x. And the thickness will be dx. And if we try to bring it out, it is something like this if we try to enlarge it. The thickness will be dx. The height will be y higher minus y lower. Okay? And its distance from the axis of rotation is actually x. Okay? So if we try to bring out the configuration on the isometric view, it should be something like this. It's just like a drum, a hollow drum, you know. A drum with a certain thickness, but there's a hollow inside of the middle. Isometric view, so this should be the height. Okay, the thickness will be the x. This is the center of rotation, and its distance, okay, from the differential area is designated by x. It is x. I place it as x. Okay. Then to visualize the volume or the computation of the volume, we cut this one into two and we try to spread out. What will come out is something like this. After spreading out, this total length is actually the total circumference. Total circumference. Okay? And the formula for taking that circumference is 2 pi times the radius of 2 pi x. The thickness is dx. This length here is y higher minus y lower. So if we now try to proceed with the solution, differential volume will be circumference and thickness times height. Assume for the meantime that this is a rectangle. So to take for the volume, to compute for the volume, you multiply this length here by this times the thickness. Circumference times thickness times height. Circumference is 2 pi x. Thickness is dx. Height is actually y higher minus y lower. Okay, equation number 1. We do not know the equivalent of y higher as a function of x for the meantime. And we do not know the equivalent of y lower also as a function of x for the meantime. So we call this equation number 1. And we will try to bring out the relation of y higher and y lower in terms of x, okay, by deriving it from the resulting right triangle that comes out from the right circular cone. This is the height of the cone. This is the radius. This is the inclined side. This point on the sloping side is actually with coordinates xy. Okay, so this length here is x. This is y. So if this is h, this should be h minus y. And this is r. Okay? This is r. We call this angle theta, horizontal line, one inclined line. If this is angle theta, this should also be angle theta. To derive the relation, take tangent of theta using the smaller right triangle. Tangent of this is opposite over adjacent. It is h minus y over x. And taking the tangent of the lower theta by using the bigger right triangle, it should be h over r. This is h over r. Then now, try now to erase this one. What will come out? H minus y over x equal to h over r. Actually, we are formulating the equation on how to take the relation of y as a function of x. Okay? And simplifying this one, this is just pure algebra. Cross multiply this one. H should be h minus y times r. Computing for y, y will be h minus h over r times x, equation number 2. So actually, this is actually y higher. This one here. Right? And for the equation of y lower, we now know the equation of this as derived from that one. Y higher is equal to h minus h over r times x, the equation of the sloping side. And the equation of this line here, it's easy, it's a horizontal line. Y lower is equal to 0. It coincides with the x-axis. So actually, there is no triangle in the bringing out of y sub L. Y sub L by inspection is actually y equal to 0, and this is actually a horizontal line. The first one, y higher, is actually sloping straight line. Sloping straight line, this is a horizontal line. Okay? Equation number 2, equation number 3. We go back to equation number 1. Okay, we substitute equation 2 and 3 to equation number 1, therefore differential volume will be equal to 2 pi x. We are following this. 2 pi x minus the value of y higher minus lower. Okay, this is h minus h over r over x minus 0. Okay, but this is now 0. We try to combine this one, so this should be 2 pi x dx. H times r is hr minus hx over r. There is a common factor h on the numerator. We bring it out. It is this. Okay. There is a common denominator r. We place it outside. This is 2 pi h over r. So what remains on the quantity is actually rx minus x squared plus quantity dx. Why there is an x? There is an x over here. We distribute it inside. So this will be Rx, okay, minus x squared plus quantity times dx. And this is now a differential equation. Okay, to take the total volume after rotating the hollow cylinder, integrate both sides. The integral of differential volume equal to 2 pi h over r, the integral from 0 to r of Rx, okay, minus x squared plus quantity dx. Volume now will be 2 pi h over r. The first one, basic. R is constant, x is variable. We bring out r, so what will come out there for the integral of x dx will be power formula, that will be x squared over 2. R x squared over 2. Second one is still under the power formula. X cubed over 3, close quantity, or close quantity with the limit from 0 to r. The integration here is not so hard. Actually, the problem is on the formulation or the setting up of the equation. Okay, substituting limits now, this is 2 pi h over r. So when x is r, the first one will be r times r squared, that will be r cubed over 2. And when x is r, this will be r cubed all over 3 minus, when we place the lower limit, there should be 0 here and there is a 0. R times 0 will be 0 and 0 over 2 will be 0, so this one is 0. Second one, 0 cube is 0, 0 over 3 is still 0, so the second part of the lower limit is also 0. So actually, the value of the lower limit has no effect on the formula, general formula. It will just be something like this. So this is 2 pi h over r. Simplifying these two fractions here, the denominator are different, so we cross multiply. Then multiply the common denominator, so this should be r cubed times 3 is 3r cubed. Okay. 2 times r cubed is minus 2r cubed. And the common denominator now will be 2 times 3, this is 6. Then to bring out the solution to be as clear as possible, you try to cancel out. So this is 2 pi h over r times the quantity. 3r cubed minus 2r cubed is r cubed, right? And r cubed will be r times r squared. And 6 is actually 3 times 2. I place like that so I could show you the cancellation. So these two here cancel with this, and these are here cancel with this. So what will remain on the formula for the volume will be, there's a 3 underneath, right? So this is 1/3 pi r squared times h. So this is the general formula for taking the volume of a right circular cone. initially, or on the first solution under the circular disk, volume is actually 1/3 pi r square h. And by using the hollow cylindrical method, supposed to be the volume will still be the same. We are deriving the same formula for taking the volume. That's the essence of mathematics. Volume now will be 1/3 pi r square h. Okay guys, that's the solution for taking or deriving the formula for taking the volume of a right circular cone by using the hollow cylindrical method. Okay, good afternoon Los Angeles.